Hey everyone. So today we're going to talk about some really interesting math concepts. Not the kind that makes you stressed about homework, just the kind where we take our time and really break things down. I want to explain these ideas slowly and clearly so you actually understand what's going on instead of just memorizing formulas. So, where do we start? Let's talk about prime numbers for a bit. You know what prime numbers are, right? They're those numbers that you can only divide by 1 and themselves. So like 2 is prime, 3 is prime, 5 is prime, 7 is prime, then 11, 13, 17, and they just keep going. There's something really interesting about prime numbers. They're like these building blocks of all numbers. Every other number can be broken down into smaller pieces, but primes just are what they are. You can't divide them any further. Now, here's where it gets interesting. Back in the year 1859, there was this mathematician named Bernhard Riemann. He was thinking about numbers, and he came up with this thing called the Riemann hypothesis. It's been unsolved for over 160 years now. Still, nobody's figured it out. What Riemann was thinking about was the pattern of prime numbers, because when you look at primes, they seem kind of random at first, like 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. The gaps between them seem to just do whatever they want. Sometimes you get two primes right next to each other, like 2 and 3, or 11 and 13. Those are called twin primes, by the way. But sometimes the gap gets bigger, like after 7 you have to wait until 11. That's a gap of 3 whole numbers. And the gaps just keep getting weirder and less predictable as you go up higher and higher. So Riemann was like, okay, maybe there's some hidden pattern here. Maybe if I look at this from a different angle, I can figure out what's actually going on with these primes. And what he did was he created this thing called the Riemann zeta function. The zeta function is just a way of taking numbers and doing operations on them, like a recipe. You put a number in, the function does its thing, and you get the number out. The way it works is pretty simple to describe, even if the math gets complicated. You take this variable, usually called s, and you basically add up 1 divided by 1 to the power of s, plus 1 divided by 2 to the power of s, plus 1 divided by 3 to the power of s, and you just keep going forever. 1 divided by 4 to the power of s, 1 divided by 5 to the power of s, on and on. Now, when I say forever, I mean literally forever. You add up infinitely many of these fractions, which sounds impossible, right? How do you add up infinite things? But mathematicians figured out how to make sense of this. When the number s is bigger than 1, this infinite sum actually settles down to a specific value. It doesn't just keep growing forever. It reaches a point where adding more terms barely changes anything. Let me give you an example. Say s equals 2. So we're looking at 1 divided by 1 squared plus 1 divided by 2 squared plus 1 divided by 3 squared, and so on. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So we get 1 plus 1 quarter plus 1 ninth plus 1 16th plus 1 25th, and we keep going. Each term we add gets smaller and smaller because we're dividing by bigger and bigger numbers. 1 divided by 100 squared is 1 divided by 10,000. That's a tiny number. 1 divided by 1,000 squared is 1 divided by 1,000,000, even tinier. So even though we're adding infinitely many terms, they get so small, so fast, that the total actually approaches a specific number. For s equals 2, that number turns out to be pi squared divided by 6, which is pretty wild. Pi shows up in this thing about fractions and squares. So that's the zeta function when s is a regular positive number bigger than 1. You can calculate it, it makes sense. But Riemann didn't stop there. He was like, what if we use other numbers for s? What if we use negative numbers? What if we use complex numbers? Oh, complex numbers. Let me tell you about complex numbers for a minute. So you know how you can't take the square root of a negative number using regular numbers? Like, what's the square root of -1? There's no regular number that, when you multiply it by itself, gives you -1. Positive times positive is positive. Negative times negative is also positive. So square root of -1 doesn't exist in the world of normal numbers. But mathematicians were like, okay, what if we just invent a new type of number? What if we just say, all right, there's this number called I, and I is the square root of -1. It's not a real number. It's an imaginary number, hence the name. They literally just made it up to solve this problem. And once you have I, you can make all these complex numbers by combining real numbers and imaginary numbers. So like 3 plus 4i is a complex number. The 3 is the real part, and the 4i is the imaginary part. You can add them, multiply them, do all sorts of math with them. They follow their own rules. And here's the thing about complex numbers that makes them cool. You can think of them as points on a plane. The real part tells you how far left or right to go, and the imaginary part tells you how far up or down to go. So 3 plus 4i is like, go 3 steps to the right, 4 steps up. -2 minus 5i is 2 steps left, 5 steps down. This is called the complex plane. It's just a way to visualize these numbers. Okay, so back to Riemann. He took his zeta function and he was like, what happens when I plug in complex numbers? What happens when S is something like 1/2 plus 14i, or -2 plus 3i, or whatever? And it turns out the zeta function can handle that. You can extend it to work with complex numbers through this process called analytic continuation, which is pretty complicated, so we're not gonna get into the details. Just know that mathematicians figured out how to make the zeta function work for complex numbers too. Now, here's where the Riemann hypothesis comes in. When you plug different complex numbers into the zeta function, sometimes you get 0 as your answer. These are called the zeros of the zeta function, the places where the function equals 0. Some of these zeros are really obvious. If you plug in -2, you get 0. -4 gives you 0. -6, -8. All the negative even integers give you 0. Mathematicians call these the trivial zeros because they're easy to find. But there are other zeros, lots of them, infinitely many of them, in fact. And they're not at simple spots like -2 or -4. They're at these weird, complex number locations, like 1/2 plus 14.13i, 1/2 plus 21.02i, 1/2 plus 25.01i. All these strange, specific places. And here's what Riemann noticed, or at least what he suspected. All of these non-trivial zeros, every single one, seemed to have a real part of exactly 1/2. Like their position on the complex plane was always at the line where the real part equals 1/2, but the imaginary part could be anything. So the Riemann hypothesis is just this statement. All the non-trivial zeros of the zeta function have a real part equal to 1/2. That's it. That's the whole hypothesis. It sounds simple when you say it like that, but nobody's been able to prove it. Nobody's been able to show that it's absolutely, definitely true for all of the infinitely many zeros. People have checked a lot of zeros, like a lot. Using computers, mathematicians have verified that the first 10 trillion zeros all sit exactly on that line where the real part equals 1/2 10 trillion. That's 10 with 12 zeros after it, and every single one of those zeros is right where Riemann said they should be. But 10 trillion isn't infinity. There are infinitely many zeros. And just because the first 10 trillion follow the pattern doesn't mean the 10 trillion and first one will. Or some zero way out there that we haven't checked yet. That's the thing about infinity. It's always bigger than whatever finite number you're looking at. So why does anyone care about this? Well, it turns out the Riemann hypothesis is connected to prime numbers. Remember how we started talking about prime numbers? The distribution of primes, the patterns they follow, All of that is tied up with these zeros of the zeta function. If the Riemann hypothesis is true, it would tell us really precise things about how primes are spaced out. It would answer questions about how many primes there are below a certain number, how big the gaps between primes can get, all sorts of stuff. There's even $1 million prize for solving it. The Clay Mathematics Institute has 7 problems they call the Millennium Prize problems. Solve one, get $1 million. The Riemann hypothesis is one of them. Only one of the 7 has been solved so far. A guy named Grigori Perelman proved something called the Poincare conjecture back in 2003. He actually turned down the $1 million, just didn't want it. But the Riemann hypothesis is still sitting there, unsolved. All those zeros lined up on their critical line, keeping their secrets. There are still mysteries out there in math, still things we don't understand. The universe of mathematics is bigger than our ability to comprehend it. Now, let's shift gears and talk about something more visual, more colorful, literally. Have you ever looked at a map, like a map of countries or states or counties? And have you noticed how they're always colored so that countries that touch each other have different colors? This is actually a mathematical problem, the 4-color theorem. And it goes like this. If you have any map at all, divided into regions, can you color it using only 4 colors in such a way that no 2 regions that share a border have the same color? Now, when I say share a border, I mean they have to have a line between them. If 2 regions just touch at a single point, like 4 states meeting at one corner, that doesn't count. They can be the same color. We're only worried about regions that have an actual boundary line between them. So, the question is, do 4 colors always work? Or is there some really complicated map out there somewhere that would need 5 colors or 6 or more? This problem was first brought up back in 1852. A guy named Francis Guthrie was coloring a map of the counties in England, and he noticed that he only seemed to need 4 colors. So he asked his brother, Frederick, who was a math student, "Hey, is this always true? Can you always color any map with just 4 colors?" Frederick passed the question along to his professor, a mathematician named Augustus de Morgan. And de Morgan started thinking about it, and he couldn't figure it out. So he mentioned it to other mathematicians, and they couldn't figure it out either. For over 100 years, this problem bounced around the mathematical community. People tried to prove it. They thought they had proofs. Then other people would find mistakes in those proofs. It was this whole back and forth thing. One guy, Alfred Kempe, published a proof in 1879 that stood for 11 years before someone found an error in it. 11 years, this thing was accepted as correct. Then Percy Hewitt looked at it more carefully and found a gap in the logic But even though Kempe's proof was wrong, it introduced some useful techniques, something called Kempe chains, which are these clever ways of swapping colors around on a map to fix conflicts. Those techniques ended up being important later on. There was another failed proof by a guy named Peter Tate in 1880. He tried a different approach, looking at edges instead of regions, treating the map as a kind of graph. That approach had problems too, but again, the ideas were useful. All these failed proofs slowly built up a toolkit of techniques and insights. People proved simpler versions of the problem, like they showed that 5 colors always work. That one's actually pretty easy to prove compared to 4 colors. They showed that you can always color a map with 6 colors. Also, not too hard, but 4 colors, that was the sticking point. Part of the problem is that there are infinitely many possible maps. You can't just check all of them. You need some kind of general logical argument that works for every single map that could ever exist. And maps can get really complicated. You can have a region that snakes around and touches lots of other regions. You can have regions completely surrounded by other regions. You can have weird shapes, peninsulas, all sorts of geographical weirdness. The breakthrough finally came in 1976. 2 mathematicians, Kenneth Appel and Wolfgang Haken, working at the University of Illinois, they managed to prove the 4-color theorem. But here's the thing, they used a computer to do it. What they did was they broke the problem down into a huge number of specific cases. They identified about 1900 different configurations of regions that could appear on a map, and they showed that if you could color each of these configurations with 4 colors, then you could color any map with 4 colors. Then they wrote a computer program to check each of those 1900 configurations. The computer churned through them one by one, checking whether 4 colors were sufficient. And it turned out they were. Every single configuration worked. So the proof relied on the computer doing all this tedious checking that would be impossible for a human to do by hand. Imagine trying to manually verify 1900 different cases, each with its own complex set of conditions and rules. It would take years, decades maybe. This caused a bit of controversy in the math community. Some people were uncomfortable with a proof that couldn't be verified by hand. Like, how do you know the computer didn't make a mistake? How do you know there wasn't a bug in the code? But over time, people got more comfortable with it. Other mathematicians checked Appel and Haken's work, verified the algorithm, ran their own versions of the computer program. In 1997, another group of mathematicians came up with a simpler proof that still used the computer, but only needed to check about 633 configurations instead of 1900. And as computer-assisted proofs became more common in mathematics, the four-color theorem became less controversial. Now it's pretty much universally accepted as true. So what did we learn? We learned that any map, no matter how complicated, can be colored with four colors so that adjacent regions have different colors. You never need a fifth color. Four is always enough. Think about that for a second. You could draw the most absurdly complex map imaginable. 1,000 regions, 10,000 regions, regions within regions, within regions, doesn't matter. Four colors will do it. There's this hidden order in the chaos, this underlying simplicity in what looks complicated. And it's interesting how the proof works too. It's not some elegant logical argument you can write out on a chalkboard. It's this brute force computer check of hundreds of cases. But that's okay. Sometimes that's how math works. Sometimes you have to just check things one by one. Now, let's talk about infinity. Because infinity is one of those concepts that seems simple at first, but gets really weird when you dig into it. What is infinity? It's just this idea of something that goes on forever, right? Never ends, keeps going and going and going. But here's where it gets strange. There are different kinds of infinity, different sizes of infinity. Some infinities are bigger than other infinities. That sounds wrong, doesn't it? Like infinity is infinity. How can one infinity be bigger than another? They're both infinite. They both go on forever. How do you compare them? Well, a mathematician named Georg Cantor figured out how to do this back in the late 1800s. He came up with a way to compare infinite sets and show that some are genuinely larger than others. Let's start with the simplest infinity, the counting numbers. 1, 2, 3, 4, 5, and so on. This set goes on forever. There's no biggest counting number. For any number you pick, you can always add 1 and get a bigger number. So the set of all counting numbers is infinite. Mathematicians have a special name for this size of infinity. They call it Aleph Null, written with the Hebrew letter Aleph and a little subscript 0. Aleph Null is the cardinality of the counting numbers, where cardinality just means the size of a set. Now, what about the even numbers? 2, 4, 6, 8, 10, and so on. This is also an infinite set, but is it the same size as the counting numbers? You might think, well, the even numbers are only half of the counting numbers, right? Like, you skip all the odd numbers, so maybe this infinity is half the size of the first infinity. But that's not how infinite sets work. The even numbers and the counting numbers are actually the same size. They have the same cardinality. Both are Aleph Null. How can we tell? Well, Cantor came up with this idea of pairing things up. If you can match every element in one set with exactly one element in another set with nothing left over on either side, then the two sets are the same size. So for the counting numbers and the even numbers, we can make a pairing. 1 goes with 2, 2 goes with 4, 3 goes with 6, 4 goes with 8. In general, the counting number n goes with the even number 2 times n. Every counting number has a partner. Every even number has a partner. Nothing is left unpaired. So the sets are the same size. Both have cardinality aleph null. This is weird, right? The even numbers are a subset of the counting numbers. They're literally contained inside the counting numbers, but they're the same size as the counting numbers. That's just how infinity works. What about the integers? That's all the whole numbers, including 0 and negative numbers. -3, -2, -1, 0, 1, 2, 3, and so on. Is this bigger than the counting numbers? Nope, same size again, aleph null. You can pair them up. 0 goes with 0, 1 goes with 1, 2 goes with -1, 3 goes with 2, 4 goes with -2, 5 goes with 3, 6 goes with -3. You keep zigzagging back and forth between positive and negative, and you can match every integer with exactly one counting number. Okay, what about fractions? Surely there are more fractions than counting numbers. Between any two counting numbers, there are infinitely many fractions. Between 1 and 2, you have 1 1/2, 1 1/3, 1 1/4, 1 1/5, all these fractions packed in there. But no, Cantor showed that the fractions, or rational numbers, as mathematicians call them, are also the same size as the counting numbers. Aleph null again. The way you show this is a little more complicated. You kind of list the fractions in a clever way, spiraling out from 0, hitting every possible fraction exactly once. It's hard to describe without pictures, but it works. You can pair up every fraction with a counting number. So we have all these different infinite sets, counting numbers, even numbers, integers, fractions, and they're all the same size, all aleph null. You might be wondering, is every infinite set the same size? Is aleph null the only infinity? And the answer is no. There are bigger infinities, much bigger. Consider the real numbers. This is all the numbers, including all the decimals, all the irrational numbers like pi and the square root of 2, everything on the number line. This set is infinite, obviously, but it's a bigger infinity than the counting numbers. Cantor proved this with something called a diagonal argument. It's really clever. You assume, just for the sake of argument, that the real numbers are the same size as the counting numbers. That means you could list all the real numbers, pairing each one with the counting number. So you start writing them out. Real number 1 might be 0.14159 and so on. Real number 2 might be 1.41421 and so on. Real number 3 is something else. You keep going, trying to list every real number. Now, here's the trick. Cantor showed you could construct a new real number that's not on your list. You look at the first decimal place of the first number on your list, and you make your new number's first decimal place different from that. Then you look at the second decimal place of the second number, and you make your new number's second decimal place different from that third decimal place of the third number. Make it different, and so on. What you end up with is a real number that differs from every number on your list in at least one decimal place. So it can't be on the list, but we assumed the list contained all real numbers. Contradiction. This means you can't actually list all the real numbers. You can't pair them up with the counting numbers. There are too many of them. The set of real numbers is uncountably infinite. This infinity is bigger than Aleph null. Mathematicians sometimes call it C for continuum, because the real numbers form a continuum, a continuous line with no gaps. And it doesn't stop there. You can make even bigger infinities. You can take the set of all possible sets of real numbers. That's bigger than the real numbers. Then you can take the set of all possible sets of real numbers. That's even bigger. You can keep going forever, building bigger and bigger infinities. In fact, there's no biggest infinity. For any infinite set, you can always construct a bigger one. Infinity itself is infinite in a way. There are infinitely many different sizes of infinity. This is what's called Cantor's theorem. The set of all subsets of any set is always bigger than the original set. So you can keep taking subsets of subsets of subsets, and you get an infinite hierarchy of infinities, each one larger than the last. Aleph null is the smallest infinity, the bottom rung on this infinite ladder. Then there's Aleph 1, which is the next bigger infinity, then Aleph 2, then Aleph 3, and so on. There's actually this famous unsolved problem related to this. It's called the continuum hypothesis. Cantor wondered whether C, the size of the real numbers, is the same as Aleph 1. Like, is the set of real numbers the next biggest infinity after the counting numbers? Or is there some infinity in between? He couldn't figure it out. Other mathematicians tried and couldn't figure it out either. Eventually, in the 20th century, a mathematician named Kurt Gödel and then later another one named Paul Cohen proved something really strange. They proved that the continuum hypothesis is independent of the standard axioms of set theory. What that means is you can assume it's true or you can assume it's false, and either way you won't run into any contradictions. It's like how in geometry you can assume parallel lines never meet, or you can assume they do meet, and you get different but equally consistent geometries. The continuum hypothesis is similar. So, in one sense, the continuum hypothesis doesn't have an answer, or it has multiple answers, depending on which version of set theory you're working in. But that's infinity for you. The more you think about it, the weirder it gets. Infinities within infinities, hierarchies of endlessness, questions that don't have single answers. Recently, mathematicians discovered two new types of infinite sets called exacting cardinals and ultra-exacting cardinals. These are infinities, so large and so strange that they don't fit neatly into the existing hierarchy. Exacting cardinals are like infinities that contain copies of themselves. Imagine a set so big that it includes complete copies of itself inside it, not just similar sets, but exact duplicates. It's like a library that contains not just books, but also complete copies of the entire library, including copies of the library that contains copies of the library, all the way down. Ultra-exacting cardinals are even weirder. They include not just copies of themselves, but also the rules for how to construct those copies. These infinities don't play nicely with some of the assumptions of mathematics. They might contradict something called the axiom of choice, which is this basic principle about selecting elements from sets. And there are probably more infinities waiting to be discovered, more weird, incomprehensible sizes of endlessness that don't follow the rules we thought they followed. Math is full of mysteries, full of unsolved problems and unexpected discoveries. The Riemann hypothesis, still waiting for a proof after 160 years. The four-color theorem, proved but only with the help of computers. The nature of infinity, constantly revealing new layers of strangeness. The unsolved problems are what keep mathematics alive, what give mathematicians something to work on, what drive the field forward. Let's think about prime numbers again for a little bit, because there's more to say about them. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47. They just exist, each one indivisible, irreducible, little atoms of the number system. Mathematicians have been studying primes for thousands of years. Ancient Greeks knew about them. Euclid proved there are infinitely many of them way back around 300 BC. His proof is really elegant. He basically said, assume there's a biggest prime, multiply all the primes together and add 1. That number is either prime itself or it's divisible by a prime that wasn't in your original list. Either way, you found a new prime. Contradiction. So there must be infinitely many primes. That's probably the oldest proof in number theory that's still taught today, over 2,000 years old, and it still works exactly the same way. But even though we know there are infinitely many primes, we don't have a formula for them. There's no equation you can plug n into and get the nth prime number. You kind of just have to check each number individually to see if it's prime. Well, there are tricks. You can eliminate obviously non-prime numbers. Anything even except 2 isn't prime because it's divisible by 2. Anything ending in 5 except 5 itself isn't prime because it's divisible by 5. You can check divisibility by small primes to rule out lots of candidates. But eventually you just have to do the work. For big numbers, this gets computationally expensive. Testing whether a really huge number is prime can take a lot of computer power. People do it anyway, though. There are these distributed computing projects where thousands of computers work together to find really big prime numbers. The biggest known prime as of 2024 has over 41 million digits. It was discovered by an amateur mathematician using a program called GIMPS, the Great Internet Mersenne Prime Search. 41 million digits. If you tried to write that number out, it would take you weeks, months probably, and it's prime, divisible only by 1 and itself. Why do people search for these massive primes? Partly because they're useful. Prime numbers are important in cryptography, in the systems that keep your online data secure. When you shop online or check your bank account, prime numbers are working in the background to encrypt your information. But partly people search for big primes just because they're there, because it's interesting, because finding a new biggest prime is an achievement, even if it doesn't have any immediate practical application. There's something very human about that, searching for patterns, pushing boundaries, wanting to know what's out there, even if there's no obvious reason to look. The primes go on forever, getting rarer as numbers get bigger, but never disappearing entirely. Somewhere out there is a prime with 1 trillion digits, a prime with 1 trillion digits. Primes so big we'll never find them, never write them down, never even think about them specifically. But they exist. They are out there in the abstract mathematical universe, being prime. Now let me tell you about Gödel's incompleteness theorems. This is about the limits of what we can prove in mathematics. There's this idea that math should be complete and consistent. Complete means that every true statement can be proven. Consistent means that you can't prove something and its opposite at the same time. Like, you can't prove that 2 plus 2 equals 4 and also prove that 2 plus 2 doesn't equal 4. That would be a contradiction. For a long time, mathematicians hoped that we could create a perfect system of axioms, basic rules that we accept as true without proof, from which we could derive all mathematical truth, kind of like building blocks. Start with a few simple, obviously true statements, and build everything else up from there through pure logic. And then this guy Kurt Gödel came along in 1931 and basically proved that this is impossible. At least it's impossible for any system complex enough to include basic arithmetic. What Gödel showed is that in any such system, there will always be true statements that can't be proven within that system. Statements that are true, but you can't get to them using just the axioms and the rules of logic you've set up. You'd need to add new axioms to prove them, but then there would be other true statements that still can't be proven, and you'd need even more axioms, and it never ends. So, mathematics is inherently incomplete. There will always be truths we can't prove, at least not from within our current framework. We can always expand the framework, add more axioms, prove more things, but we'll never get everything. There will always be more true statements lurking just beyond our reach. That's the first incompleteness theorem. The second one is even more mind-bending. It says that no consistent system can prove its own consistency. Like, you can't use the rules of math to prove that the rules of math don't lead to contradictions. You'd need to step outside the system to do that. So there's this uncertainty built into mathematics. We can't be completely sure our axioms are consistent. We believe they are because we haven't found any contradictions yet, but we can't prove it using the axioms themselves. Math keeps working though. We keep discovering new theorems, solving problems, building theories. The incompleteness doesn't stop us. It just means we have to accept that mathematics is bigger than our ability to formalize it completely. There's always more, always another layer, always truths beyond our current reach. Let's shift gears and talk about fractals. We're gonna look at shapes that have this property called self-similarity. A fractal is a shape that has self-similarity at different scales. When you zoom in on a part of a fractal, you see structures that look similar to the whole thing. Zoom in more, and you see similar structures again and again and again. The pattern repeats infinitely as you zoom deeper and deeper. One of the simplest fractals is called the Sierpinski triangle. You start with the solid triangle, then you remove the middle triangle, the one that connects the midpoints of the three sides. Now you have three smaller triangles. Then you do the same thing to each of those three triangles. Remove the middle triangle from each one. Now you have 9 even smaller triangles. Then you repeat the process on all 9. Then on all 27, then on all 81. You keep doing this forever, removing middle triangles at every level. What you end up with is this intricate, lacy pattern. Lots of empty space, but also lots of tiny triangles arranged in this perfectly self-similar way. Zoom in on any part of it, and you see the same pattern at a smaller scale. The Sierpinski triangle has some weird properties. It has zero area because you keep removing triangles forever, taking away more and more of the original triangle's area. But it has infinite perimeter because every time you remove a triangle, you create more edges, and this process never stops. Zero area, infinite perimeter. It's like a one-dimensional curve in some sense, even though it's made of two-dimensional triangles. It exists in this weird in-between space, dimensionally speaking. In fact, fractals often have non-integer dimensions. The Sierpinski triangle has a dimension of about 1.585, measured using something called the Hausdorff dimension. Not quite two-dimensional like a normal shape, not quite one-dimensional like a line, somewhere in between. This is what fractals do. They break our usual intuitions about dimension and space. They occupy these strange intermediate realms, more complex than simple curves, but less solid than filled in shapes. And they show up in nature. Coastlines are fractal-like, with bays and inlets at every scale. Mountains are fractal, with large peaks and valleys that contain smaller peaks, and valleys that contain even smaller ones. Trees branch fractally, each branch splitting into smaller branches that split into even smaller branches. Clouds, river networks, blood vessels, snowflakes, all fractal in their structure. Nature loves self-similarity. Even the distribution of galaxies in the universe shows fractal patterns at large scales. Clusters of galaxies, clusters of clusters. The cosmic web of matter arranged in this intricate, self-similar foam. Fractals are everywhere once you start looking for them, and they all come from simple rules applied recursively. Take a shape, apply a transformation, repeat. That's it. That's all you need to generate infinite complexity. The Koch snowflake is another classic fractal. You start with an equilateral triangle. Then, on each side of the triangle, you add a smaller equilateral triangle, 1/3 the size of the original sides, sticking out from the middle. So now you have a 6-pointed star kind of shape. Then you repeat the process on each of the 12 edges. Add even smaller triangles to each edge. Then repeat again and again forever. The perimeter of the Koch snowflake grows without bound. It gets longer and longer with each iteration, approaching infinity, but the area stays bounded. It converges to 8/5 of the original triangle's area. So you have an infinite perimeter surrounding a finite area. These fractals are interesting to think about. The repetition of simple rules, the emergence of pattern from process, the infinite detail hiding in finite space. You could sit and watch a fractal being generated, iteration after iteration, watching the complexity build, each step following inevitably from the last. No randomness, just deterministic unfolding of structure. And yet, the final result, after infinitely many iterations, is something impossibly intricate, more detail than you could ever fully perceive or describe, infinite information encoded in a finite space. Now, let's think about chaos theory for a minute. This is related to fractals in some ways. Chaos theory studies systems that are sensitive to initial conditions. The classic example is the butterfly effect. The idea that a butterfly flapping its wings in Brazil could theoretically set off a chain of events that leads to a tornado in Texas. The point isn't that butterflies literally cause tornadoes. The point is that tiny differences in the starting conditions of a complex system can lead to huge differences in the outcome. Weather is like this. The atmosphere is a chaotic system. You can't predict the weather perfectly more than a week or two in advance, because any tiny error in your measurements of current conditions will get amplified over time, making your predictions less and less accurate. This isn't because we don't know the laws of physics. We understand the equations that govern air pressure and temperature and wind. The problem is that those equations are nonlinear and highly sensitive to initial conditions. Even with perfect knowledge of the laws, we can't predict the long-term behavior because we can't measure the initial conditions with infinite precision. And this is true of lots of systems. Double pendulums swing chaotically. 3 or more objects orbiting each other under gravity move chaotically. Fluid flow becomes turbulent and chaotic. Ecological systems with predators and prey can show chaotic population dynamics. Chaos is everywhere, lurking in systems that seem like they should be predictable but aren't. And yet, within the chaos, there are patterns. Chaotic systems often settle into what are called strange attractors. These are shapes in the system's state space that the system tends to orbit around or spiral into. The most famous strange attractor is the Lorentz attractor, which looks like a butterfly with 2 loops. The system traces out this intricate path, looping around one side, then suddenly switching to the other side, then back again, never quite repeating, but always staying within the same general butterfly-shaped region. These attractors are often fractal. They have self-similar structure at different scales, so chaos and fractals are connected. Chaos generates fractals, and fractals describe chaos. It's all part of the same mathematical landscape. Complexity emerging from simplicity, unpredictability from deterministic rules, order from disorder, disorder from order. The universe is full of this kind of thing. Simple laws leading to complex behavior. The whole being greater than the sum of its parts. Emergence, they call it. Properties that exist at higher levels of organization but can't be predicted just from knowing the lower level rules, like consciousness emerging from neurons, or life emerging from chemistry, or ecosystems emerging from individual organisms interacting. Math shows us that this is possible, that simple rules can generate unbounded complexity, that determinism doesn't imply predictability, that order and chaos can coexist and even depend on each other. Let me tell you about topology for a bit. This is the study of shapes and how they can be deformed. In topology, two shapes are considered the same if you can smoothly deform one into the other without cutting or gluing. So a circle and an oval are the same topologically. You can squish a circle into an oval. A sphere and a cube are the same. You can smooth out the corners of a cube until it becomes a sphere. But a sphere and a torus, which is a donut shape, are different. You can deform a sphere into a torus without punching a hole through it, and that counts as cutting, which isn't allowed in topology. So topologists care about properties that stay the same under smooth deformations. Things like how many holes a shape has. A sphere has no holes. A torus has one hole. A two-hole torus, which looks like a figure-8 donut, has two holes. You can't change the number of holes by stretching or bending, so this is a topological property. There's a famous joke that a topologist can't tell the difference between a coffee cup and a donut because a coffee cup has one hole, the handle, and a donut has one hole, the hole in the middle. So topologically, they're the same shape. You could imagine molding a clay donut into a coffee cup shape without tearing the clay or sticking parts together. Topology is a weird and abstract field, but it's useful. It helps us understand the structure of space itself. In general relativity, space-time is curved and warped by mass and energy, and topology helps describe the possible shapes of the universe. Is the universe finite or infinite? Does it wrap around on itself like the surface of a sphere? Is it flat or curved or multiply connected in weird ways? These are topological questions, and we don't know the answers yet. The universe is too big, and our measurements aren't precise enough. But topology gives us the language to ask the questions and think about the possibilities. There's something called algebraic topology, which uses algebra to study topological spaces. You assign algebraic objects like groups or rings to shapes, and then you can use algebraic techniques to tell shapes apart. It's abstract and technical, but it's powerful. One result from algebraic topology is the hairy ball theorem. This says that you can't comb the hair on a sphere flat everywhere. There has to be at least one point where the hair sticks up, or where the combing creates a cowlick or whorl. Think about the wind patterns on Earth. The Earth is roughly a sphere, and wind is like combing, a direction at each point. The hairy ball theorem says there must be at least one point where the wind speed is 0, a stationary point, and indeed, these exist. They're called cyclones and anticyclones, places where the wind circulates around a central calm point. That's topology predicting something about meteorology, math connecting to the physical world in unexpected ways. Or think about the Brouwer fixed point theorem. This says that if you take a disk, like a circular piece of paper, and you crumple it up and put it down on top of where it started, at least one point will end up directly above where it started. It might have moved, but it's still over its original position. This seems obvious, maybe, but it's not trivial to prove, and it has applications. Fixed point theorems are used in economics to prove that equilibrium prices exist in markets. They're used in game theory to prove that certain games have Nash equilibria, stable strategies where no player wants to change their move. Topology, this abstract study of shapes and deformations, connects to economics and game theory. Math is all interconnected like this. Fields that seem totally unrelated turn out to use the same underlying ideas. Number theory and complex analysis connecting through the Riemann zeta function. Topology and algebra connecting through algebraic topology. Chaos theory and fractals connecting through strange attractors. Graph theory and map coloring connecting to the four-color theorem. It's all one big web of ideas, each supporting and illuminating the others. You pull on one thread and the whole tapestry shifts. And we're just scratching the surface, just peeking at the edges of this vast landscape of mathematical truth. There are whole regions we haven't mentioned. Differential equations, which describe how things change over time. Probability theory, which deals with randomness and uncertainty. Statistics, which lets us make sense of data. Linear algebra, which studies vectors and matrices and transformations. Each of these is its own world, with its own techniques and results and unsolved problems, and they all overlap and interact in complex ways. You could spend lifetimes exploring mathematics and never see all of it, never even see a significant fraction of it. The territory is too vast, the landscape too complex, and new mathematics is being created all the time. Mathematicians are proving new theorems, discovering new structures, inventing new tools and techniques. The frontier of knowledge keeps expanding. So there's always more, always new mysteries to contemplate, new ideas to explore, new connections to discover. Let's think about symmetry for a little while. Symmetry is this idea of things staying the same under transformations. A circle has rotational symmetry. You can rotate it by any angle around its center, and it looks exactly the same. A square has rotational symmetry too, but only at specific angles. 90 degrees, 180 degrees, 270 degrees. Rotate it by those amounts and it looks unchanged. But rotate it 45 degrees and it's clearly different. A snowflake, or at least the idealized mathematical version of a snowflake, has six-fold symmetry. Rotate it by 60 degrees and it looks the same. 120 degrees, 180, 240, 300, all work. This is rotational symmetry. But there are other kinds of symmetry too. Reflection symmetry, where you can flip something across a line or plane and it looks the same. A butterfly has bilateral symmetry. Flip it left to right and it's unchanged. Humans have approximate bilateral symmetry too. Your left side is roughly a mirror image of your right side. Some shapes have translational symmetry. You can slide them along by a certain distance and they look the same. An infinite tiling pattern can have translational symmetry. Wallpaper patterns often do. And then there are more abstract symmetries. Symmetries in equations, in physical laws, in algebraic structures. Physicists care a lot about symmetry. The laws of physics have certain symmetries built into them. They're the same everywhere in space, which is translational symmetry. They're the same at all times, which is temporal symmetry. They're the same in all directions, which is rotational symmetry. And these symmetries lead to conservation laws. Noether proved this back in 1915. It's called Noether's theorem. For every continuous symmetry in the laws of physics, there's a corresponding conservation law. Translational symmetry in space leads to conservation of momentum. Translational symmetry in time leads to conservation of energy. Rotational symmetry leads to conservation of angular momentum. So the fact that the universe looks the same from one place to another means that momentum is conserved. Energy can't be created or destroyed because the universe looks the same at different times. Angular momentum is conserved because the universe doesn't have a preferred direction. This is profound. Symmetry and conservation are two sides of the same coin. The deep regularities in nature connect to the invariances in the laws. And mathematicians study symmetry abstractly through something called group theory. A group is a set of symmetries along with a way to combine them, like the symmetries of a square. You can rotate by 90 degrees, or flip horizontally, or do both in sequence. The set of all possible symmetries, with the operation of doing one after another forms a group. Groups can be finite or infinite, simple or complicated. There are groups with exotic structures and unexpected properties, and group theory is used everywhere in math, in number theory, in geometry, in algebra, in topology. Groups are one of the most important structures in all of mathematics. There's even something called the classification of finite simple groups, which is this massive project that took decades and hundreds of mathematicians to complete. They classified all the basic building blocks of finite groups. Turned out there are 18 infinite families of groups, plus 26 weird exceptional groups that don't fit into any family. These exceptions are called the sporadic groups. The largest sporadic group is called the monster group. It has about 8 times 10 to the 53 elements. That's a number with 54 digits, an unimaginably huge group with deep connections to other areas of math like modular forms and string theory. The monster group is this bizarre, isolated structure sitting out there in the mathematical landscape. Nobody invented it or constructed it for any practical reason. It was discovered, predicted to exist based on other mathematical considerations, and then found, and it turned out to be real. This gigantic symmetry group with no obvious geometric interpretation, but tons of interesting properties. And there are connections, mysterious connections, between the monster group and modular forms and something called monstrous moonshine, which relate the dimensions of certain representations of the monster to coefficients in a modular form. Nobody knows why this connection exists. It just does. Two completely different areas of math, linked by this strange numerical coincidence that turned out to be not a coincidence at all, but a deep relationship we still don't fully understand. That's math for you. Connections everywhere, often in the most unexpected places. The monster group talking to modular forms, talking to string theory, talking to who knows what else. Everything intertwined in this incomprehensibly complex web of relationships. And we've barely scratched it, barely seen the smallest corner of the whole picture. There's so much more. Lie groups and Lie algebras, algebraic geometry, representation theory, homological algebra, categories and functors and natural transformations, whole fields of mathematics that most people have never heard of, where researchers spend their careers exploring intricate abstract structures, proving theorems, building theories, and it all fits together somehow, all connects, all makes sense from the right perspective, even when that perspective is so high level and abstract that it's barely recognizable as math anymore. Category theory, for instance, that's math about math. Instead of studying mathematical objects, you study the relationships between different mathematical structures. You abstract away from the specific details of numbers or shapes or spaces, and you just look at the patterns of how things relate to each other. It's so abstract that it's sometimes called abstract nonsense, but it's powerful. It reveals deep similarities between different areas of math. It shows that concepts that seem totally unrelated actually share the same underlying structure. This happens over and over in mathematics. You start with something concrete, like numbers or shapes. You abstract away the details, find the essential pattern. Then you realize that same pattern shows up somewhere else in a totally different context. And then you've unified two areas of math, shown they're secretly the same thing in disguise. Like how complex numbers and two-dimensional vectors are secretly the same, or how matrix multiplication and function composition follow the same rules, or how integration and antiderivatives are inverse operations, two ways of looking at the same thing. Math is full of these unifications, these moments where disparate ideas turn out to be facets of a single underlying truth. And that suggests that maybe deep down, all of math is one thing, one vast interconnected structure that we perceive as many different fields only because we're looking at it from different angles. Maybe there's a grand unified theory of mathematics, like physicists dream of a grand unified theory of physics, one framework that encompasses everything, one set of axioms from which all mathematical truth flows. Or maybe not. Maybe math is genuinely plural, genuinely diverse, multiple independent structures coexisting in the abstract realm. We don't know, and maybe we can't know. But it's interesting to think about, to wonder about the unity and diversity of mathematics, the way simple ideas generate complexity, the way abstract patterns reveal hidden connections, the way everything fits together in this intricate, beautiful, inexhaustible tapestry of truth. Now let's talk about the number pi for a little bit, because pi is everywhere and it's really interesting. Pi is the ratio of a circle's circumference to its diameter. Every circle, no matter how big or how small, has this same ratio. The distance around the circle is always pi times the distance across it. This makes pi a geometric constant. It's built into the fabric of space itself, at least into flat Euclidean space. In curved spaces, like on the surface of a sphere or in the geometry near a black hole, the ratio can be different, but in normal flat space, it's always pi. 3.141519653589793, and it keeps going. Trillions of digits have been calculated. The decimal expansion never ends, never repeats. Pi is irrational. You can't write it as a fraction. There are no two integers you can divide that will give you pi exactly. You can approximate it. 22/7 is pretty close. 3.142857, which rounds to 3.14. Not bad. 355 over 113 is even closer. 3.141599. The first 6 digits match pi exactly, but none of these are exactly pi. They're just approximations. Pi itself is this infinite, non-repeating decimal that can never be written down completely. And yet, we use it all the time. In formulas for circles, spheres, cylinders, in trigonometry, in calculus, in physics. Wave equations involve pi. The distribution of primes involves pi through the Riemann zeta function. Pi shows up in the most unexpected places. Probability theory uses pi. The Gaussian distribution, the bell curve, has pi in its formula. Why does the geometry of circles connect to the statistics of random events? It's mysterious, but there it is. Buffon's needle problem is a classic. You drop a needle onto a floor with parallel lines. The probability that the needle crosses a line involves pi. You can actually estimate pi by dropping needles and counting how many cross lines. The more needles you drop, the better your estimate. This is called a Monte Carlo method, using randomness to estimate mathematical constants. It's not the most efficient way to calculate pi, but it's one of the most elegant, and there are formulas for pi that are just beautiful. One of them is pi over 4 equals 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, continuing forever, alternating signs, dividing by odd numbers. It's called the Leibniz formula. It converges to pi over 4 incredibly slowly. You need thousands of terms to get even a few digits of accuracy, but the fact that it works at all is amazing. This simple pattern of adding and subtracting fractions somehow encodes the geometry of circles. There's another formula, the Basel problem. 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, continuing forever, equals pi squared over 6. Euler solved this in the 1700s. The sum of the reciprocals of the squares equals pi squared divided by 6. Why? How does adding fractions connect to pi? It's through complex analysis and the zeta function and connections that aren't obvious at all, but they're real. The formulas work. Pi is woven into the mathematical fabric in deep and subtle ways. You can define pi without reference to circles at all. You can define it through infinite series or through trigonometric functions or through complex analysis. It emerges naturally from the structure of mathematics itself. Pi is inevitable. You can't do mathematics without encountering it eventually. It's just there, built into the logical structure of numbers and space and functions. And we've calculated it to trillions of digits, not because we need that many digits. We don't. Even for extremely precise scientific calculations, a few dozen digits of pi are more than enough. We calculate more digits because we can, because it's a challenge, because it pushes the boundaries of computational mathematics, and maybe because there's something satisfying about knowing more of pi, like we're peeling back layers of an infinite mystery, seeing more and more of this endless decimal expansion. We'll never see all of it, can't see all of it. It's infinite, but we can see more, always more, just like mathematics itself. Always more to discover, always more to understand, always more truth waiting just beyond our current knowledge. The digits of pi extend infinitely. 3.15, each digit determined, not random, fully determined by what pi is, but unpredictable without calculation. You can't guess the millionth digit of pi. You have to compute it, and people do. Enthusiasts memorize thousands of digits of pi. The record is over 70,000 digits recited from memory. Why? Not for any practical reason, just because it's an achievement, because it's possible. Mathematics is full of these things, knowing more digits of pi than anyone else, finding bigger prime numbers, proving theorems that have no applications. And that's okay. Beauty doesn't need to be useful. Truth doesn't need to serve a purpose. They're valuable in themselves. Pi is interesting because it is what it is. This constant, this bridge between geometry and analysis, this infinite, non-repeating number that shows up everywhere. 3.14159. The first few digits almost everyone knows. The beginning of an infinite journey into numerical precision. And beyond those familiar digits, trillions more, each one exact, determined. Pi is what connects circles to all these other areas of mathematics. It's this hub in the network of mathematical ideas. Let me tell you about one last thing. Euler's identity. A lot of people call it the most beautiful equation in mathematics. E to the power of pi times I plus 1 equals 0. 5 mathematical constants. E, the base of natural logarithms, pi, which we just talked about, I, the imaginary unit, 1 and 0, and this equation connects all of them. This simple, elegant relationship. E is about growth and decay, compound interest, population dynamics, anything that grows or shrinks exponentially. Pi is about circles and geometry and waves. I is about rotation in the complex plane, about numbers that don't exist on the real line. 1 and 0 are the multiplicative and additive identities, the most basic numbers, and they all come together in this one equation. E raised to an imaginary power involving pi equals -1. Add 1 to both sides and you get 0. Why does this work? It comes from complex analysis. When you generalize exponential functions to complex numbers, you get this deep connection between exponentiation and rotation. E to the power of I theta traces out points on the unit circle in the complex plane. As theta goes from 0 to 2 pi, e to the I theta goes all the way around the circle. When theta equals pi, you're at the opposite side of the circle from where you started, the point -1. So e to the I pi equals -1. This equation is actually just describing a geometric fact about rotation in the complex plane. But that doesn't make it any less beautiful. If anything, understanding where it comes from makes it more beautiful. This deep connection between exponentials, circles, and imaginary numbers, all part of the same mathematical tapestry. Keith Devlin, a mathematician, wrote about Euler's identity. He said it reaches into the very depths of existence, connecting these concepts in a way that seems almost miraculous. And it does feel profound that mathematics has this much structure, this much interconnectedness, that you can write down one simple equation and have it encapsulate so much. But maybe it's not miraculous. Maybe it's just how mathematics is. Everything connected, everything flowing from the same logical foundations. We see different parts of math as separate because we study them separately. Geometry here, algebra there, analysis over there. But really, it's all one thing, one vast unified structure. And Euler's identity is a window into that unity, a glimpse of how everything fits together. E to the I pi plus 1 equals 0. 7 symbols, 5 constants, deep beauty. The math is all around us, all interconnected, all flowing from simple principles into complex structures. The Riemann hypothesis with its mysterious zeros, the four-color theorem with its maps and regions, the different sizes of infinity stacking upward endlessly, the fractals with their infinite detail, the chaos hidden in simple rules, the topology of space, the symmetries and groups, the constants like pi and e, the beautiful connections like Euler's identity, all of it part of the same mathematical reality, all of it true, all of it there. And before we wrap up, let me tell you about the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. Each number is the sum of the two before it. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. Such a simple rule, but it generates this sequence that shows up everywhere in nature. The spirals in seashells, the arrangement of leaves on a stem, the branching of trees, the pattern of seeds in a sunflower. And if you divide each Fibonacci number by the one before it, you get ratios that approach the golden ratio: 1.618033988. 13 divided by 8 is 1.625. 21 divided by 13 is 1.61538. 34 divided by 21 is 1.61904. The ratios get closer and closer to the golden ratio as you go further in the sequence, approaching it, converging on it, never quite reaching it exactly, because the Fibonacci numbers are integers and the golden ratio is irrational, but getting arbitrarily close. The golden ratio itself is this special number. If you have a rectangle where the ratio of length to width equals the golden ratio, and you cut off a square, the remaining rectangle also has its sides in the golden ratio. This property makes it unique. It's the most irrational number in a technical sense. It's the hardest number to approximate with fractions. And it shows up in art, in architecture, in nature. The Parthenon in Athens has proportions related to the golden ratio. Renaissance paintings use it. The spiral of galaxies approximates it. Whether this is intentional design or just human perception finding patterns, or genuine mathematical principles underlying natural forms, nobody's quite sure. Probably some combination of all three. But the golden ratio is there. 1.618, a number with its own special properties, its own beauty, its own place in the mathematical landscape. And the Fibonacci sequence, this simple pattern of adding the last two numbers to get the next, generates it, approaches it, points toward it. Everything connected, simple rules generating complexity, patterns within patterns within patterns. One more thing. Let me tell you about zero. Zero seems so simple. Nothing, the absence of quantity. But zero is actually one of the most profound concepts in mathematics. Ancient civilizations didn't always have zero. The Romans didn't have a symbol for it. Their number system went from one straight to the next without acknowledging nothing as a number. It was mathematicians in India who first treated zero as a number in its own right. Around the 5th or 6th century, they gave it a symbol, a placeholder in their base 10 system, and they allowed it to be used in calculations. Zero changes everything. With zero, you can have place value systems. The difference between 1 and 10 and 100 is just where you put the zero. Without zero, notation gets incredibly complicated. Zero also lets you have negative numbers. The number line extends in both directions, from zero, positive on one side, negative on the other. Zero is the boundary, the balance point, and zero has its own arithmetic properties. Add zero to anything and it stays the same. Zero is the additive identity. Multiply anything by zero and you get zero. This simple rule has profound consequences throughout mathematics. Dividing by zero is where things get weird. You can't do it, or rather, it doesn't make sense in the usual arithmetic. If you divide 10 by 2, you get 5, because 5 times 2 equals 10. But what times 0 equals 10? There's no number that works. Anything times 0 is 0. So, division by 0 is undefined. It's a hole in arithmetic, a place where the usual rules break down. Unless you step outside ordinary arithmetic. In some extended number systems, you can have infinities and infinitesimals and make sense of division by 0 in certain contexts. But in ordinary arithmetic, it's just not allowed. And that's okay. Mathematics doesn't have to answer every question. Some things are undefined, and that's part of the structure. 0 is nothing and everything. The absence that makes presence possible. The placeholder that enables positional notation. The boundary between positive and negative. The additive identity. The absorbing element in multiplication. All these roles, all these properties wrapped up in a single concept, 0. This idea of nothing being something, of absence being present, of 0 being a number. It's almost paradoxical, but it works. It's consistent, it's useful, and it's beautiful in its way. 0, the number that represents nothing but means everything. Another piece of the mathematical tapestry, another thread in the infinite web of concepts and relationships. So that's what we've covered: the Riemann hypothesis and prime numbers, the 4-color theorem, different types of infinity, Gödel's theorems about incompleteness, fractals, and chaos, topology, symmetry and groups, pi and e, and Euler's identity, Fibonacci numbers and the golden ratio, 0, all these different areas of mathematics, all interconnected, all part of the same vast structure of truth and beauty. Mathematics is this huge landscape. We've just taken a walk through a tiny part of it, looked at some interesting sights along the way, thought about some profound ideas. There's so much more out there, so many more theorems to discover, so many more patterns to find, so many more connections to make. But we've seen enough to get a sense of it, the beauty, the complexity, the elegance, the mystery. Math is bigger than any of us, older than humanity. It'll outlast everything. The truths of mathematics are eternal, and we get to be part of it, get to think about it, get to appreciate it, get to marvel at the patterns and the proofs and the profound connections between seemingly unrelated ideas. That's pretty cool. So thanks for coming along on this journey through some complex math theories. Hope you learned something. Hope you saw mathematics in a new light. Hope you appreciated the slow, careful explanation of these ideas. Mathematics is worth taking your time with, worth really thinking about, worth understanding deeply, rather than just memorizing formulas. And that's what we did here. Took our time, explained things slowly and clearly, made sure the ideas made sense before moving on. That's how you really learn math. That's how you really appreciate it. So keep exploring, keep thinking, keep asking questions. There's always more to discover in the world of mathematics. Always more beauty waiting to be found. Now let me tell you about something really cool called the Mandelbrot set. This is an infinitely complex fractal that comes from a really simple equation. You take a complex number c and you plug it into this equation z squared plus c, where you start with z equals 0. So you calculate 0 squared plus c, which just equals c. That's your new z. Then you calculate that squared plus c. And you keep doing this over and over. For some values of c, this process stays bounded. The numbers you get don't shoot off to infinity. They just kind of bounce around in a limited area. For other values of c, the numbers explode and get infinitely large. The Mandelbrot set is the set of all values of c, where the process stays bounded. And when you graph it on the complex plane, coloring points black if they're in the set and other colors, based on how quickly they escape to infinity, you get this incredibly intricate, beautiful shape. It has these bulbous regions connected by thin filaments, little spirals and tendrils extending out in all directions. And here's the wild part. As you zoom in on any edge of the Mandelbrot set, you see more and more detail. The complexity never ends. You can zoom in forever and keep finding new structures, new patterns, new tiny copies of the whole set embedded in the boundaries. This infinite complexity comes from such a simple rule: z squared plus c, repeated over and over. That's it. And somehow that generates this shape that contains infinite information, infinite detail, infinite beauty. The Mandelbrot set has become this iconic image in mathematics and computer graphics. Those psychedelic posters with the intricate fractal patterns, a lot of those are zoom-ins of the Mandelbrot set or similar fractals. And it's another example of how math can surprise you, how simple rules can create unimaginable complexity, how infinity lurks in unexpected places. You could spend your whole life exploring the Mandelbrot set, zooming deeper and deeper into its boundaries, and you'd never see all of it. There's always more, always another layer of detail. That's true of mathematics in general, really. You could spend multiple lifetimes studying math and never run out of things to learn. There are entire branches of mathematics, entire theories and frameworks that even professional mathematicians don't fully understand because they're outside their specialty. Number theory, where we think about primes and the Riemann hypothesis. Topology, where we think about shapes and surfaces and how they can be deformed. Graph theory, where we think about networks of connections. Group theory, where we study symmetry. Differential geometry, where we study curved spaces. Category theory, which is like math about math, studying the relationships between different mathematical structures. Each of these fields is vast. Each one has its own unsolved problems, its own deep questions, its own infinite landscapes to explore. And that's kind of overwhelming if you think about it too hard. But it's also exciting. There's always more to learn, always another mystery to contemplate. The universe of mathematical truth is inexhaustible. Let's talk about the concept of proof for a minute, because in mathematics, it's not enough to just observe that something seems to be true. You have to prove it with absolute certainty. A mathematical proof is a logical argument that starts from accepted axioms and uses valid rules of inference to arrive at a conclusion. If the proof is correct, the conclusion is guaranteed to be true, not just probably true or likely true, but absolutely, certainly true. This is what separates mathematics from experimental science. In science, you can never be completely certain. You gather evidence, you test hypotheses, but there's always the possibility that new evidence will overturn your conclusions. In mathematics, once something is proved, it's proved forever. The Pythagorean theorem was proved over 2,000 years ago, and it's still just as true today as it was then. But proving things can be really hard. Sometimes the statement you're trying to prove seems obviously true, but finding a rigorous proof is incredibly difficult. Take Fermat's last theorem. This says that there are no three positive integers a, b, and c that satisfy the equation a to the n plus b to the n equals c to the n for any integer value of n greater than 2. For n equals 2, you get the Pythagorean theorem, and there are lots of solutions. 3 squared plus 4 squared equals 5 squared. 5 squared plus 12 squared equals 13 squared. Lots of examples. But Fermat claimed that for n equals 3 or 4 or 5 or any number bigger than 2, there are no solutions. No whole numbers that make the equation work. He wrote this in the margin of a book in 1637 and added a note saying he had a proof, but the margin was too small to contain it. Then he died without ever writing down the proof. Mathematicians spent over 350 years trying to prove or disprove Fermat's last theorem. Some of the greatest mathematical minds in history worked on it. Partial results were obtained. Specific values of n were proved, but a general proof for all n remained elusive. Finally, in 1994, a mathematician named Andrew Wiles announced a proof. He had worked on it in secret for 7 years, using incredibly sophisticated techniques from algebraic geometry and number theory. The proof was over 100 pages long and required knowledge of fields of mathematics that didn't even exist in Fermat's time. When the proof was first announced, it had a gap, an error that Wiles had to fix. He worked with a colleague, Richard Taylor, for another year to patch the hole. In 1995, the corrected proof was published, and Fermat's last theorem became Fermat's last theorem no more. It was now a proven fact. This is the nature of mathematical research. Problems that seem simple can require centuries of work and incredibly deep techniques to solve. And when they're finally solved, it's a triumph of human intellect and persistence. Let's think about the concept of dimensions for a bit. We live in a three-dimensional world, up and down, left and right, forward and backward. 3 independent directions of movement. But mathematically, you can have any number of dimensions. A line is 1-dimensional. A plane is 2-dimensional. Our space is 3-dimensional. But there's no reason to stop there. A 4-dimensional space would have 4 independent directions. We can't visualize this because our brains evolved in a 3-dimensional world, but we can work with it mathematically. We can define points in 4-dimensional space using 4 coordinates. We can define distances and angles and all the usual geometric concepts. And we can keep going. 5-dimensional space, 6-dimensional, 100-dimensional, 1,000,000-dimensional. There's no limit In some areas of physics, particularly string theory, the universe might actually have more than 3 spatial dimensions. The extra dimensions might be curled up so small that we can't perceive them, but they could still exist and have real physical effects. In mathematics, high-dimensional spaces are studied all the time. In statistics, if you're analyzing data with 100 different variables, you're essentially working in a 100-dimensional space. Each variable is a dimension, and there are surprising results about high-dimensional spaces. Things that are true in 3 dimensions aren't necessarily true in higher dimensions. Spheres in high dimensions behave weirdly. Most of the volume of a high-dimensional sphere is concentrated near its surface, not in the center. The number of corners on a hypercube, which is the higher dimensional analog of a cube, grows exponentially with dimension. A square has 4 corners. A cube has 8. A 4-dimensional hypercube has 16. A 5-dimensional hypercube has 32. Each time you add a dimension, you double the number of corners. High-dimensional geometry is strange and counterintuitive, but it's mathematically rigorous and well understood, even if we can't visualize it. This is another example of how mathematics goes beyond what we can perceive or experience directly. We can reason about things we can't see or touch or imagine visually. As long as the logic is sound, the mathematics is valid. Let's talk about probability for a minute. This is a whole field of mathematics dealing with randomness and uncertainty. The basic idea is pretty simple. If you flip a fair coin, the probability of getting heads is 1/2. If you roll a fair 6-sided die, the probability of getting any particular number is 1/6. But probability gets complicated quickly. Consider the birthday problem. In a room with 23 people, what's the probability that at least 2 of them share a birthday? Most people guess it's pretty low. 23 people, 365 possible birthdays. Seems like the chances would be small, but actually the probability is just over 50%. More than half the time in a group of 23 people, at least 2 will share a birthday. This seems wrong at first, but when you work through the math, it makes sense. You're not asking for a specific pair of people to share a birthday. You're asking for any pair. And with 23 people, there are 253 different pairs. That's a lot of chances for a match. This is called the birthday paradox, though it's not really a paradox. It's just counterintuitive. Probability is full of results like this. Things that seem like they should be rare turn out to be common. Things that seem likely turn out to be unlikely. The Monty Hall problem is another famous example. You're on a game show. There are 3 doors. Behind one is a car. Behind the other 2 are goats. You pick a door. The host, who knows what's behind each door, opens one of the other doors to reveal a goat. Then he offers you a chance to switch your choice to the remaining unopened door. Should you switch? Most people think it doesn't matter. You're choosing between two doors, so the probability should be 50-50 either way. But that's wrong. You should switch. If you switch, your probability of winning the car is 2/3. If you stay with your original choice, your probability is only 1/3. This seems impossible, but it's true. The key is that the host's action of opening a door and revealing a goat gives you information. He's not opening a door at random. He's deliberately showing you a goat. This changes the probabilities in a subtle way. When you first picked a door, you had a 1/3 chance of being right. That means there was a 2/3 chance the car was behind one of the other two doors. When the host opens one of those doors and shows you a goat, that 2/3 probability doesn't disappear. It gets concentrated on the remaining unopened door. So, by switching, you're effectively getting the benefit of having picked two doors instead of one. This problem has confused a lot of people, including professional mathematicians. But the math is clear. Switching is the better strategy. Probability teaches us to be careful about our intuitions. What seems obvious isn't always true. You have to work through the math to be sure. Let's think about prime numbers one more time, because there's something really interesting about how they're distributed. The prime number theorem says that the number of primes less than some number x is approximately x divided by the natural logarithm of x. So, if you want to know roughly how many primes there are below 1 million, you calculate 1 million divided by the natural log of 1 million. The natural log of 1 million is about 13.8. So 1 million divided by 13.8 is about 72,000. And it turns out there are exactly 78,498 primes below 1 million. So the approximation is pretty close. As x gets larger, the approximation gets better and better. For really big numbers, x divided by ln x is an excellent estimate of the number of primes below x. This theorem was conjectured by Gauss and Legendre in the late 1700s based on numerical evidence, but it wasn't proved until 1896, over 100 years later, independently by Jacques Hadamard and Charles de la Vallée-Poussin. The proof uses complex analysis and properties of the Riemann zeta function. It's not simple, but the result is beautiful. This simple formula captures the density of primes, and it tells us something interesting. Primes get rarer as numbers get bigger, but only logarithmically so. The average gap between primes near x is approximately ln x. So near 1 million, primes are spaced about 13 or 14 apart on average. near 1 trillion, they're spaced about 27 or 28 apart. This is a slow growth. Even for astronomically large numbers, primes are still reasonably common. They never disappear completely. They just spread out gradually. There's something comforting about that. The primes are always there, always present, just less densely packed as you go higher. Now, let me tell you about mathematical notation, because the way we write mathematics affects how we think about it. Early mathematicians didn't have good notation. They wrote everything out in words. Imagine trying to solve an equation by writing the unknown quantity multiplied by itself equals 9. It's cumbersome. The development of symbolic notation was a huge advance, using x for an unknown, using plus and minus and equals signs, using exponents to indicate repeated multiplication. This notation makes patterns visible. You can see at a glance that x squared plus 2x plus 1 equals the quantity x plus 1 squared. Try writing that out in words and the relationship is much less obvious. Good notation makes some problems trivial that would be hard without it. Roman numerals are terrible for arithmetic. Try multiplying MCM XLIV by LXV7. It's a nightmare. But multiply 1944 by 67 using Arabic numerals, and it's straightforward. The same numbers, the same mathematical operation, but one notation makes it easy and the other makes it nearly impossible. Mathematicians are always inventing new notations. Summation notation with the sigma symbol, product notation with the pi symbol, integrals with the elongated s, set builder notation with curly braces. Each notation captures a different pattern, makes a different kind of thinking easier, and sometimes the notation suggests new mathematics. When Leibniz invented calculus, his notation of dy over dx for derivatives suggested thinking of derivatives as ratios of infinitesimally small quantities. This led to manipulations that were technically not rigorous but gave correct results. It took a couple hundred years to make the foundations of calculus fully rigorous, but Leibniz's notation was so useful that people kept using it anyway. Notation matters. It shapes how we think. It makes some ideas natural and others difficult. Good notation is part of what makes mathematics powerful. Let's talk about mathematical beauty for a minute. Mathematicians often talk about proofs or theorems being beautiful, but what does that mean? Beautiful mathematics tends to be elegant, simple ideas that have profound implications, unexpected connections between different areas, proofs that are short and insightful rather than long and computational. Euler's identity is beautiful because it connects 5 important constants in one simple equation. The proof that there are infinitely many primes is beautiful because it's short and clever and uses such a simple idea. The symmetry groups are beautiful because they capture deep structure in simple terms. But beauty in mathematics isn't just about simplicity. Sometimes complexity itself can be beautiful, like the intricate structure of the Mandelbrot set, or the elaborate architecture of a detailed proof. There's something aesthetic about mathematics, not just utilitarian. Mathematicians don't just want true results, they want elegant results. They want proofs that illuminate why something is true, not just verify that it is. Paul Erdős, a prolific mathematician, used to talk about the book, an imaginary book kept by God containing the most elegant proof of every theorem. When he found a particularly beautiful proof, he'd say it was from the book. This sense of mathematical beauty is real. It's not just subjective preference. Mathematicians from different cultures and different eras tend to agree on what's elegant and what's clunky. There seems to be an objective aesthetic quality to mathematics, and pursuing beauty often leads to good mathematics. When you try to find the most elegant way to prove something, you often discover new techniques or new connections. The search for beauty drives mathematical progress. Let me tell you about the concept of infinity again, but from a different angle. We talked about different sizes of infinity earlier, but there's also the concept of infinity as a limit. When you calculate the area under a curve using calculus, you're essentially adding up infinitely many infinitesimally thin rectangles. Each rectangle has width approaching 0, and there are infinitely many of them. But the sum converges to a finite value, the area under the curve. This is using infinity as a tool, a way of thinking about limits and continuous change. You imagine a process carried out infinitely many times, or carried to an infinite extreme, and see what value it approaches. The derivative in calculus is similar. You want the slope of a curve at a point, but a single point doesn't have a slope. You need 2 points to define a slope. So you take 2 points very close together and calculate the slope between them. Then you imagine bringing the points closer and closer together, approaching 0 distance. The slope approaches a limiting value, and that's the derivative. This idea of approaching but never quite reaching, of getting arbitrarily close without arriving, is central to calculus and analysis. It lets us make sense of instantaneous rates of change, which seem paradoxical if you think about them too hard. How can something be changing at an instant when an instant has 0 duration? But through limits and infinity, we can make it rigorous. we can define precisely what we mean by instantaneous rate of change, and it works. Calculus is one of the most powerful tools in all of mathematics, used everywhere in science and engineering, all built on this idea of infinity as a limit, as something approached but never reached. Now, let's think about the concept of proof by contradiction. This is where you assume the opposite of what you want to prove, show that leads to a contradiction, and conclude that your assumption must have been wrong. Euclid's proof that there are infinitely many primes uses this technique. Assume there's a finite list of all primes. Multiply them all together and add 1. That number is either prime or composite. If it's prime, you found a prime not on your list, contradiction. If it's composite, it has a prime factor, which must not be on your list because dividing by any listed prime leaves remainder 1. Contradiction. Either way, your assumption was wrong. So there can be a finite list of all primes. This is such a powerful technique. Sometimes it's much easier to show that something can't be false than to directly show it's true. The proof that the square root of 2 is irrational uses contradiction. Assume it's rational, so you can write it as a fraction a over b in lowest terms. Square both sides. 2b squared equals a squared. This means a squared is even, so a is even, so a equals 2c for some integer c. Substitute back. 2b squared equals 4c squared. Simplify. B squared equals 2c squared. So b squared is even, so b is even. But we said a over b was in lowest terms, and now both a and b are even. Contradiction. So the square root of 2 can't be rational. These proofs have an elegance to them. You don't construct the answer directly, you trap it logically, showing that any alternative leads to absurdity. Mathematics is full of clever argument techniques like this. Proof by induction, where you show something is true for one case, and that if it's true for any case, it's true for the next. So it must be true for all cases. Proof by contrapositive, where you prove the logically equivalent statement that if not B, then not A, instead of if A, then B. Each technique is a tool in the mathematician's toolkit. Different problems call for different approaches, and part of the art of mathematics is choosing the right approach, seeing which technique will crack a particular problem. Sometimes you have to try several before you find one that works. Let me tell you about one more concept before we finish up: the idea of abstraction in mathematics. Mathematics keeps abstracting, keeps generalizing, keeps finding the essential pattern beneath the specific examples. You start with counting apples, then you realize the number 3 doesn't depend on whether you're counting apples or oranges or rocks. You've abstracted away from the physical objects to the pure concept of quantity. Then you realize you can extend numbers beyond counting fractions, negative numbers, real numbers, complex numbers. Each extension abstracts further, generalizing the concept of number. You start with triangles and circles. Then you abstract to general shapes. Then to topological spaces where you don't care about distances or angles, just about connectivity and continuity. Then to even more abstract structures. This process of abstraction is what makes mathematics so powerful. By stripping away the irrelevant details, you reveal the essential structure, and that structure often applies in many different contexts, not just the original one. Group theory is an abstraction of symmetry, but once you have the abstract concept of a group, you find groups everywhere. The symmetries of shapes, yes, but also the structure of number systems, the solutions to equations, the transformations in quantum mechanics. The abstraction lets you prove theorems about groups in general, and those theorems automatically apply to all these different contexts. This is why mathematics can be so hard to learn. You're not just learning facts, you're learning to think abstractly, to see patterns at higher levels of generality. But it's also why mathematics is so beautiful and so powerful. One abstract theorem can unify dozens of specific results. One general principle can apply in countless situations. Mathematics is the science of patterns, and abstraction is how we discover which patterns are truly universal. So that's our journey through complex math theories, explained slowly and carefully. We covered a lot of ground: prime numbers and the Riemann hypothesis, the four-color theorem, different sizes of infinity, Gödel's incompleteness, fractals and chaos, topology, symmetry, the constants pi and e, Euler's identity, Fibonacci numbers, the Mandelbrot set, mathematical proof, dimensions, probability, mathematical notation, beauty in mathematics, abstraction. All these topics interconnected, all part of the vast landscape of mathematics. And we've only scratched the surface. There's so much more. But hopefully this gave you a sense of what mathematics is really about. Not just calculations and formulas, but deep ideas and beautiful patterns and surprising connections. Mathematics is worth taking your time with, worth really thinking about, worth understanding deeply. So keep exploring, keep asking questions, keep thinking about these ideas. There's always more to discover. Let's spend a little more time thinking about numbers and how they work in different systems. We usually use base 10 for our numbers because we have 10 fingers, but computers use binary, base 2, just zeros and ones. And this actually tells us something interesting about numbers themselves. When you write the number 42 in base 10, you're really saying 4 10s plus 2 1s. 42 equals 4 times 10 plus 2 times 1. In binary, 42 would be 1 0 1 0 1 0. That's 1 32 0 16s 1 8 0 4s 1 2 and 0 1s. 32 plus 8 plus 2 equals 42. Same number, different representation. The number 42 exists independent of how we choose to write it down. The representation is our choice, but the number itself is a mathematical object that just is what it is. This might seem like an obvious point, but it's actually pretty deep. Numbers have this Platonic existence. They're not invented by humans, they're discovered. The number 3 existed before anyone counted to 3. The number pi existed before anyone measured a circle. And this raises interesting philosophical questions. Where do numbers exist? What are they exactly? Are they real in the same way that rocks and trees are real? Most mathematicians are Platonists in their working life. They talk about discovering theorems, not inventing them. They talk about mathematical objects as if they exist somewhere, independent of human minds. But some mathematicians and philosophers are nominalists or formalists. They argue that mathematics is just a game of manipulating symbols according to rules. The symbols don't refer to anything real, they're just marks on paper or thoughts in our heads. These debates have been going on for thousands of years and probably won't be settled anytime soon. But it's interesting to think about. Regardless of whether numbers really exist in some metaphysical sense, they certainly behave as if they do. The facts about numbers are objective. 2 plus 2 equals 4 for everyone, everywhere, always. Mathematical truths don't depend on opinion or culture or perspective. And that's remarkable. In a world where so much is subjective and relative, mathematics gives us absolute certainty about at least some things. Let's talk about one more fascinating area: game theory. This is the mathematical study of strategic decision making. The simplest game is rock, paper, scissors. Each player chooses one of 3 options simultaneously. Rock beats scissors, scissors beats paper, paper beats rock. If both players choose the same thing, it's a tie. What's the optimal strategy? Well, if you always play rock, your opponent will figure that out and always play paper. If you try to be clever and predict what your opponent will do, they might predict your prediction and counter it. The optimal strategy is to randomize. Choose each option with equal probability, 1/3 each. That way, your opponent can't exploit any pattern in your play. This is called a mixed strategy Nash equilibrium. It's named after John Nash, who proved that every finite game has at least one Nash equilibrium, a stable strategy where no player can improve by changing their choice given what the other players are doing. Game theory gets much more complex than rock, paper, scissors. The prisoner's dilemma is a famous example. Two prisoners are questioned separately. Each can either cooperate with the other by staying silent or defect by betraying the other. If both cooperate, they each get a light sentence, say 1 year. If one defects and the other cooperates, the defector goes free and the cooperator gets 10 years. If both defect, they each get 5 years. What should you do? Well, if your partner cooperates, you should defect to get 0 years instead of 1. If your partner defects, you should also defect to get 5 years instead of 10. So, no matter what your partner does, defecting is better for you. But here's the problem. Your partner is thinking the same thing. So you both defect and get 5 years each, when you could have both cooperated and gotten only 1 year each. This is a dilemma. Individual rationality leads to a worse outcome for both players. The Nash equilibrium is to both defect, even though mutual cooperation would be better. This models lots of real-world situations. Arms races between countries, competing businesses, choosing whether to cooperate or compete aggressively. Environmental issues where individual self-interest leads to collective harm. Game theory gives us tools to analyze these situations, to understand why certain outcomes occur even when they seem suboptimal, and sometimes to design mechanisms that encourage better outcomes. It's mathematics applied to human behavior and strategic interaction, and it's incredibly useful in economics, political science, biology, computer science, and many other fields. Now, let's think about the concept of randomness for a minute. What does it mean for something to be random? If you flip a fair coin, each flip is independent and unpredictable. There's no pattern, no way to determine in advance what the outcome will be. That's random. But if you flip a coin 1,000 times, you'll get close to 500 heads and 500 tails. The individual flips are random, but the aggregate behavior is predictable. This is the law of large numbers. Random processes have statistical regularities, even though individual outcomes are unpredictable. And here's something weird. Truly random sequences are hard to recognize. If you ask someone to write down a sequence of coin flips, they'll usually avoid long runs of the same outcome. They'll write H, T, H, T, H, T, H, H, T, or something with lots of alternation. But a truly random sequence will have runs. It'll have stretches of 5 or 6 heads in a row. It might have 20 heads in a row if you flip long enough. That seems non-random, but it's actually exactly what you'd expect from randomness. Humans are bad at generating randomness and bad at recognizing it. We see patterns where there are none and miss the statistical regularities that do exist. This is why statistics and probability are so important. Our intuitions about randomness are often wrong. We need mathematical tools to reason correctly about uncertain situations. And randomness itself is a deep concept. Is the universe fundamentally random at the quantum level, as quantum mechanics suggests? Or is there some deeper deterministic layer we haven't discovered yet? These are open questions that bridge mathematics, physics, and philosophy. Let's think about the concept of dimensions one more time, but from a different angle. We said you can have spaces with any number of dimensions, but there's also the concept of fractional dimensions, which is where fractals come in. A line is one-dimensional, an area is two-dimensional, but something like the Sierpinski triangle, with zero area but infinite perimeter, is somewhere in between. Its Hausdorff dimension is about 1.585. What does it mean to have a fractional dimension? It's a measure of how the structure fills space. A line doesn't fill any area at all. A filled square completely fills an area. The Sierpinski triangle is more than a line, but less than a filled area, so its dimension is between 1 and 2. This concept of dimension is more subtle than just counting how many independent directions you can move. It's about scaling behavior, about how the structure changes as you zoom in or out. And it turns out that fractional dimensions are all around us in nature. Coastlines, clouds, mountains, river networks. All these natural structures have fractal properties and fractional dimensions. The dimension can tell you things about the structure. A coastline with a higher fractal dimension is more jagged and irregular. A lower fractal dimension means it's smoother. This is another example of how mathematics lets us quantify and study things that seem too irregular or complex to describe precisely. Fractals and fractal dimension give us tools to talk rigorously about natural shapes that don't fit into classical geometry. Let me tell you about one more thing: the concept of continuity in mathematics. A function is continuous if small changes in the input produce small changes in the output. There are no sudden jumps or breaks. This seems like a simple idea, but making it rigorous requires care. What exactly do we mean by small changes? How small is small enough? The formal definition involves limits and epsilon delta arguments and can be quite technical, but the intuition is clear. You can draw the graph of a continuous function without lifting your pen from the paper. Continuity is important because it's a kind of smoothness or predictability. If a function is continuous, you know that nearby inputs give nearby outputs. There are no surprises, no discontinuous jumps. And continuous functions have nice properties. The intermediate value theorem says that a continuous function on an interval takes on every value between its minimum and maximum. If it's above 0 at one point and below 0 at another, it must cross 0 somewhere in between. This seems obvious, but it requires proof and relies on the completeness of the real numbers. It's not true for functions on the rational numbers, for instance. Continuity is one of the central concepts in analysis, the branch of mathematics that studies functions and limits and infinite processes. It's the foundation for calculus, differential equations, much of modern mathematics, and the concept has been generalized in many ways. Topological spaces have a notion of continuity that doesn't require numbers or distances, just the structure of open sets. Category theory has a notion of continuity that applies to morphisms between abstract structures. Mathematics keeps finding the essential pattern and abstracting it, applying it in new contexts. That's been a theme throughout this discussion. Mathematics is about finding patterns, abstracting them, generalizing them, seeing how they connect to other patterns. The Riemann hypothesis connects prime numbers to complex analysis. The four-color theorem connects graph theory to topology. Infinity connects set theory to logic to analysis. Fractals connect geometry to dynamics to chaos theory. Symmetry connects geometry to algebra. Probability connects counting to analysis to measure theory. Everything is connected. Pull on one thread and you find it's woven through the entire tapestry. And that's what makes mathematics so beautiful and so powerful. It's not a collection of isolated facts. It's a unified whole, a single vast structure with countless aspects and perspectives. We've explored many of those aspects today, taken a long, slow tour through some of the beautiful ideas in mathematics. Try to explain them clearly and carefully, giving you time to really understand what's going on. Mathematics is deep. There's always more to learn, more to discover, more to appreciate. But hopefully, this has given you a taste of what's out there. The elegance, the surprise, the profound connections between seemingly different ideas. Keep thinking about these things. Keep asking questions. Keep exploring. Mathematics is a vast landscape, and we've only walked through a small corner of it. But every journey has to start somewhere. So, thanks for joining me on this one. Hope you learned something. Hope you see mathematics a little differently now. Hope you appreciate the depth and beauty of these ideas. There's always more to discover in the world of mathematics. Always more beauty waiting to be found. Always more truth waiting to be uncovered. And that's pretty amazing.